Okay, so good afternoon, everybody. So last time, what I did last time, I told you here, let me come here, yeah. Okay, so as I told you guys, all this course is about ones and zeros, digital system, okay? This course, we are gonna design, okay, digital circuit to do something, okay? For example, I'm going to design a circuit to do addition, multiplication by the hardware. So the hardware can do addition, multiplication, whatever. And these are the basic component for computers or microprocessors. Because computers or microprocessors, when you write your program in C or Java or whatever, it has to be translated to machine code. And the machine code has to be translated by the hardware. So eventually, it has to be done by the hardware, okay? So the purpose of this course in general is to learn how the hardware can do computations that's needed to create computers or digital system in general, okay? So I told you also before, we have three main types of gates, okay? So we have AND, we have AND gate, OR gate, also we have inverter, okay? These are the basic ones. We can create everything from these basic ones, as I told you before. Also in this course, you are not gonna see voltage because this is not an electronic course, electronics. It's just you will see zeros or ones, but in reality, these zeros or ones are translated to voltage, and the electronic circuit is gonna do the same logic we have here in the truth table. And then also last time I told you, we are gonna create more gates, okay? So for example, last time I explained NAND, and that's what we are gonna do in the coming lab. We are gonna do NAND, but also I told you, if you look, this NAND is actually created from the basic ones here, using the basic ones, because this NAND is actually X prime or Y prime. Is that okay? It's actually, or you can see it in a different way. You can see it like AND. This AND is followed by inverter, okay? But we are going to use it like one gate. We call it NAND, okay? The other one, NOR, I explained last time, which is actually similar. Every time you see this bubble, as I told you before, this is an inverter, okay? So this is actually like OR, and then followed by inverters. That's why if you look at the truth table here, and you compare this truth table with the truth table of OR, you find it is flipped, okay? Every bit here is flipped because we put inverter after OR. And then I'm gonna use it like one gate, okay? Also, we have exclusive OR, as I explained to you before, and this is symbol we are gonna use for exclusive OR, as I told you. If you wanna build the exclusive OR from the basic gates, you can see it is XY prime or X prime Y, okay? And I told you, to make it easy, if you look here, exclusive OR, if the two inputs are equal, either both of them are zeros or ones, we are gonna get zero. So this one is gonna give you zero when the two inputs are equal. Otherwise, it's gonna give you one. And then what I did here, I used the same exclusive OR, but I put inverter after it. And that's what we call exclusive NOR, not OR, NOR. That's why you can see here this bubble. So this bubble means it's inverter. Okay, that's why you can see here. And usually exclusive OR, this is the symbol we use for exclusive OR. So if you can see the relation between exclusive OR and exclusive NOR, just inverter here, okay? And how this is the truth table. Also these gates are created from the basic ones. We are going to use them as standalone, as a gate, okay? So, and you will see it right now. And I told you, someone can ask me, okay, so we don't need new gates. I can create everything from the basic ones, the three basic ones. I don't need NAND, I didn't need NOR, okay? I agree, we can create everything from the basic ones, I agree. However, as you will see in this course, why we like NAND, how NAND is useful, how NOR is useful, okay? You will understand in this course, using NAND, we can create the three basic ones. So here you can see using NAND, I can make AND gate. Okay, I can make inverter. Just tie the input this way. The NAND becomes inverter. Also, I can create OR gate. Okay. So for how this one is OR, very simple. I'm gonna tell you how. For this is inverter, so this is A prime and this is B prime, and the output here is actually A prime and B prime. Everything is inverted because this is NAND. So if you apply De Morgan, as I explained before, it becomes A or B. So this is equivalent to OR. Okay, what is the fancy? What is the fancy thing about this? The fancy thing is, if you have a good electronic circuit for NAND, I can make the whole computer or the whole circuit all using NAND. And that's what we are gonna explain in this course later. So instead of using 3 different gates, maybe electronics don't like it. Okay, maybe for electronics it's better if you have only 1 gate and just repeat it. Okay, that's why this is the importance of NAND. Same thing for NOR, by the way. Same thing for NOR. Using NOR, I can create the 3 gates, so I can make OR, I can make NOT, also I can make AND. Okay, and same thing, I can create, if you have a circuit, and this circuit has the 3 basic operations, I can create it using only NOR. Any questions? Okay. One more thing, as you start to see in labs, we have logic chips. For example, here, 74 family. We can have in this chip, you can see here, we have OR, 4 ORs, 4 OR gates. We have here 6 inverters in this chip. Okay. We have some chips here. These chips have NOR, NAND here. This chip here has XOR, 4 XOR, and we have NOR. This chip has AND, 4 AND, and so on. Okay, and you are gonna start in this lab. You are gonna start using. Already used some of them before, but we are gonna use more in this lab and coming lab. Any questions? One more thing here I want to teach about it, because when we talk about chips like this one, it's very recommended to look at the data sheet. So I posted the data sheet for each one. Using the data sheet, number one, you can find a diagram like this one. You can see how can you connect if I want to use any NAND here, as I told you. By the way, before I forget, because some of you may not read my emails, I made a video for lab 3, okay, to explain some parts of the lab, that because you don't have background, or you're still in the very beginning in electronics, in circuit, something like that, and that's totally understandable. So I don't want you to understand the details. Just for example, if you have an LED, you should know how to use it, but how it works, that's you are going to learn later. Okay, but anyway, so just I want to make sure. If you have any problem or understanding lab number 3, I made a video, just watch it, okay? if you need it. So what I was explaining here is, using the data sheet, you can know this is pin number ground here. You can put here 5 volt, and then I can see which pins are. For example, if I wanted to use this one, you have 4. They are separate. You can use 1, you can use 2. They are separate. There's no relation between them. They are separate, okay? But you need to connect ground and VCC before you use any one of these, okay? Anyway, so from here you can know these are the input and these are the output here. These are pins. One more thing, when you read the data sheet, gives you information about too many things, like propagation delay, noise margin, and all of these things. One of the important things here, I want you to understand, these logic chips are actually, they have family. They come in different families, okay? So that's what I want to tell you here, okay? For example, and usually, for example, when you read the data sheet, it's going to tell you, for example, this is CMOS or MOSFET or TTL or ECL. So what this means? Okay? So we name these families based on that electronic technology used to create them. Okay, so as you will understand, as you will see in electronics, CMOS is a transistor. It's a type of transistor. MOSFET is a type of another transistor. This one here we use what we call bipolar transistor, something like that. Okay. So anyway, so when you see, that's what I want to tell you. Okay. Don't worry about the details now, but when you see something like this is a TTL family, ECL family, or MOSFET family, or CMOS family. So this can tell you what technology used in the electronic circuit. And usually, as I'm saying here quickly, this one is very popular. We have been using it for 50 years. This one is actually high speed. This one is a very good thing about this one. It's low power consumption. And this is started to be very dominating now. So because, you know, many of the devices we are using needs powered by a small battery, right? So I like it if it is not going to consume too much power. I like the battery can last for longer time. Okay. Anyway, so one of the things, as I told you, you can see in the data sheet, you can see something related to power dissipation. Also, you can see something related to propagation delay. I think for propagation delay, simply how much time. So for example, if I do AND here, you know, in AND, if I put here 1 and 0, I'm going to get 0. But so how much time is going to get, how much time is going to take until the electronics, transistor open, transistor close, whatever, until you get the result here. That's what we call propagation delay. You understand what I'm saying? Don't think you just put 1 0, you're going to get 0 immediately. That's not true. It takes some time. This time maybe nanosecond or whatever. Okay, so that's what we call propagation. Last time I explained what I mean by noise margin. Also, there is some terms you can find in the data sheet, something like fan out and fan in. I think already in one lab you had something related to fan out. So the idea of fan out is if you have a gate here this way, how many gates I can connect here? So for example, this one can come here. I can put here input to another gate, input to another gate. How many? Is that unlimited? No, it is limited. Why? Because you have limited current here, and every input here needs some amount of current. So that's what we call fan out. So if the fan out 5, that means you can't connect more than 5 gates here after this gate. Anyway, so any questions? The last thing here also I want to teach the connection between logic and electronics. Okay, so what we have, I think what we have done so far in labs is, and that's what usually I explain all the time, is when I say 0, logic 0, it means 0 volt. When I say logic 1, I mean 5 volt. Okay, so that's what I explained, or that's what you use. This is called a positive logic. This is very popular system. Usually we do this way. However, in some chips, maybe it is using negative logic. So what negative logic means here? Oops. Negative. Yeah. So as you see here, in case of negative logic, here again we have 0 volt and we have 5 volt. But I'm gonna use the 0 volt, and we have 5 volt. But I'm gonna use 0 volt for logic 1, and I'm gonna interpret for the 5 volt like logic 0. You got what I'm saying? It doesn't matter. I have 2 values. It can be 7 and 9, any 2 values. Okay. I'm gonna interpret one of them as logic 0 and one of them like logic 1. Okay, and that's it. And then when you use the circuit, you are gonna get the same truth table we have. Okay. So anyway, most of the chips are actually positive logic, but I want you to understand, just in case in the future you see something like negative logic, you understand what it means. Okay. Any questions? Yes. Can you raise your? Okay, but you need to be careful here. Negative, it doesn't mean it is negative voltage. Okay, negative here, negative means you flip the logic. Our negative means the low voltage, which is 0, I'm going to consider logic 1. And the high voltage, I'm going to consider it logic 0. Both of them can be positive voltage. So negative here, it doesn't mean it's a negative voltage. It doesn't mean that, okay? Anyway, so you want to say, so what you want to say in some cases, I'm not sure your point here is, you want to say some cases we want to, negative logic is used for some reason. Anyway, so what I'm telling you, you should understand what positive logic means and what negative logic means. And most of the time, I think we are going to use a positive logic for all the chips we have. The second thing here, so you see here in this chapter, I started with a Boolean algebra. So I give you several expressions here or theorems. And then I told you, you should know this theorem as I told you. You should know how can you use them. So I make a summary here, and I told you in exams, anything, I'm gonna give you this slide. And I told you that here in this chapter, in this section, I talked about equivalence. Equivalence means what it means. It means, can you prove this one is equal to this one? That's the meaning of equivalence. That means if you have to, if I implement this circuit using this expression, or I implement it using this expression, I'm going to get exactly the same result as I said before. That's what the meaning of equivalent, okay? And then I told you, in order to prove this one is equal to this one or this one equal to this one, what I did here, that's what I explained last time. What I did here, I can use the Boolean, I can do algebra manipulation, as I explained last time, to prove these two expressions are equal. You should understand what do you mean by two, what it means when I say two expressions are equal. It means they have exactly truth table here, okay? So when this input, both of them are gonna give the same output. If for any input, both of them always is gonna give the same output, okay? And I told you if you want, so this is the meaning of equivalence. And I told you if you want to prove the equivalence, you can do it using algebra manipulation, or you can do it using truth table. In exam and quizzes, if I don't tell you how, you can use any one of them. Is that okay? But I'm expecting you should know both of them. How can you do manipulation, algebra manipulation, and also how can you do a truth table, okay? For example, here, I want to see if F1 is equivalent to F2. That's what I explained last time as well. So for example, using truth table. So when I did the truth table, I find they are not equivalent. Why they are not equivalent? Look here. This is okay. Oh, I found one difference here. So they are not the same. They are not equivalent, okay? Even I told you in exams, anything, don't to continue. Once you find one that's not equal, don't continue. There is no need to continue, okay? Anyway, and then last time I told you we can do algebra manipulation to simplify expressions. And simplification is very important thing. But I want you to understand what I mean by simplification. I mean, because we are gonna use it all the time. I mean, for example, here, you have this circuit here, you have this logic circuit, and this one is actually equivalent to this one. They are the same. So that means this one and this one, they are going to give you exactly same results. Okay. So which one is better for me? For sure, usually I'm looking for a simplified one. So for sure, this one is much better. Why this one is much better? For two reasons. Number one, I'm going to use less number of gates, as you see here. That means it's going to be less expensive, which is very good. Sometimes the simplified one is going to be faster. Okay. I think to understand it better, I think I have here a nice figure to tell you. It's going to come later anyway. Okay, but yeah. For example, if I compare these two circuits, for example, okay, which one is faster? I want you to understand this concept because it's still important, okay? Which one is faster? So you have to, this is what we call a critical path. You have to create what we call a critical path. Okay. So here, in order to get the result here, so I have to see what is the longest path, not the shortest one. Okay. So in order to get the result here, this one has to finish work. This one has to finish work. This one has to finish work. So I have to wait three propagation times. What I'm saying? For sure, you cannot use this path. You can't use this path because it's a small one. Usually the output here is going to depend on the longest path. Okay. But if you look at this circuit here, yeah, this one will be faster because the path here is going to be only 2 propagation time, but here it is 3. You understand what I'm saying? So that's why we need simplification. That's why once you design a circuit, you need to simplify. You understand what I'm saying? So how we are going to do simplification? Because this is a very important topic. We are going to do it in 2 different ways. In this chapter, I'm going to do it one way. In next chapter, I'm going to do it in a different way. Both of them are exactly the same thing, but as you will see, next chapter will be easier than using. So here, that's what I'm saying here. You need to understand what I mean by simplification, why you need simplification. Also, you need to understand I can do simplification by 2 approaches. One is using algebra manipulation. The second one is using key maps. Okay. In this chapter, I'm going to explain this one. Next chapter, I'm going to explain this one. Okay. So let's start with this one. Here, all what I'm going to do here, I'm going to just use the theorem I explained here. The theorem I explained in this section. Okay. The Boolean algebra theorem. I'm going to use them to do the simplification. You got what I'm saying? You know what this one is similar to, for example, in normal algebra, when I tell you y equal to x plus 5 minus whatever 3x plus 20, something like that, I ask you to simplify it. So you can just add some terms together to simplify it. Okay. Anyway, it's almost the same thing, but here we are using logic. Okay. So let's start with this one first. Here, I want to simplify. And usually key maps is easier. Okay. So I want to simplify this one. I want to use the theorem I used before. Look here. You need to think a little bit. How can you do it? But I'm going to give you some tricks. One of the tricks, always look for common part. Okay. Sometimes if one part is common, sometimes it helps you. Sometimes it doesn't make a difference. Okay. But let's see, for example, here. So here, if I want to do a simplification here, I notice this part here has xyz is here, and this one has x bar bar z as well. Okay, so I can take this part to common, and then what's remaining here is y prime. What's remaining here is y, as you see here. So here, so I can these 2 terms here. This is the opposite of distribution. Okay, for example, if you have 5x plus 2, you do distribution. Now I'm doing the opposite. There is a common factor. I'm getting it out, as you see here. But again, when you don't understand me wrong, I'm not saying every time you find a common factor, take it out. It may not help you. That's what I'm saying. But in this time, it's going to help me. Why is going to help me? Because as you see here, after I take this part out, I got here y or y prime. And y or y prime is 1. And one and anything is the same thing. So by this way, I was able to simplify 2 terms into only one term. Any questions? I'm going to give you more examples for sure. Any questions? Yeah, sure. Sorry, speak again. Yeah, because this one is equivalent to this one. So the first one here is for this expression. Okay, this one for the simplified one. Which one is that? Faster? Yeah. This is the simplified one. But if you look, so this one here, if I want to make a comparison, this one uses less number of gates. So regarding number of gates, this one is better. If you look at speed, maybe both of them in this case have the same speed, because if you look at the path here, so it's going to be this path. It's the same thing here. This is the path. So this one is going to go through three gates. So I need propagation time here, propagation time here. This is the longest path, okay? Same thing here, 1, 2, 3. So regarding speed, it's the same in this case. But I'm gonna save gates. But always we look for the simplified ones, always, okay? Any questions? Let's have more example. Let's look at this example here. Also, I notice we have a common part here, which is A prime. So I can take it out. So after I take it A prime here, okay, this is gonna help me again. It's not always, you have to think about any common part, and then you have to think, this helping me or not. In this case, it's gonna help me. Why? Because after I take this one out, I'm gonna have this one here. And you know, as I said before, anything or one is actually one. So this one should give you one, right? And one and anything is the same thing. So A prime and one is actually A prime. Okay. Same thing here. For example, here we have YZ. YZ is common. YZ here, and we have YZ here. If I take it common, so I'm gonna have here X or X prime, which is one. I'm gonna get YZ. That means here in this example, that means this circuit here, which I draw this way, is equivalent to this one. They are the same. For sure, this one will be much faster, or it's going to be faster than this one, because you're only one gate, but here it has to be two. Anyway, so let's have more example. How can we do algebra, Boolean algebra manipulation? How can we do that? Let's have more examples. For example, here, if I give you something like that and I want to simplify, so we have here this term or this term and this whole term or this term this way. So if you notice, I can notice something here very important that's going to help me. If you notice here, this term is actually, this term here is identical to this term, okay? So I'm going to call this one Y, I'm going to call this one Y as well, okay? So, or if I call, or if you call everything here, if you call everything or Y, so this one should be Y prime, because you know there is a prime here. So if you can do it in either way. So you can call this one Y, okay, and this one Y prime, or you can say this is Y. If this is Y, okay, so this one is Y prime, because one has inverter, the other one doesn't have inverter. Anyway, so now the equation becomes something like that. And you should be, this is one of the theorem you have, by the way, okay? If you have this one, the result should be X or Y, okay? And then I'm gonna tell you why. Why this one here is actually equivalent to X or Y. This one of the theorem I explained to you before, but simply I can even prove it quickly now. So it's Y or Y prime or X, sorry, and X, or and. Yeah, so no, sorry. So it's gonna be Y, yeah, or Y prime X. Is that okay? So one of the things is very, I told you before, because this one, we don't have a similar one in normal algebra, you will forget, okay? So here I can do distribution here, okay? We don't have this one in normal algebra. So if you have 2 plus 3 plus X something, or 3 times X, okay? I can't distribute this one this way. We don't have this one, but we have it here. So what I'm gonna do here, I'm gonna just do distribution. So this one should equal Y or Y prime, okay? And with Y, Y or X, okay? I just do distribution, distribute this one to these two, okay? And then here, this one becomes, as you see here, this one becomes 1. So it's gonna be X plus 1, okay? This one of the theorem you have anyway. So all what I did, because we have a big term here, I just call it this one Y and X, whatever. And then the result should be X plus Y. X, and then this is X, so I'm gonna put it here. This is Y, I'm gonna put it here. Is that okay? Any questions? Let's have more examples. Again, look at this one here. I can have observation here. This term is similar to this term. So I can call this one X and I can call this one X. And I see this term is actually, and this term are the same, but this one of them is inverter, okay? Inverter of the other. So if I call this one Y, this one becomes Y prime. Okay, so if you look at this one here and look, if you check the theorem I explained to before, so this is uniting theorem as I told you before. So if you have something like that, the result is actually X. Okay, you have already this one in the theorem I explained to before. So all what you have to do, just the result is equal to X, you just take this one, put it here. Let's have more examples. Okay, let's have more examples here. Okay, so I want to simplify this one here. Always try to look for something common, as I told you. So I can see here xz is common in all of them. So this one has xz, xz. So I'm gonna take common, as you see here, and then after that you can also notice here. This one has W, this one has W, and it's gonna very good for me to take it common, right? So that's what I did. So I took W here common. Okay, why it's good for you? Because I'm gonna have here Y prime or Y. Y prime or Y is actually 1. So as you see here, it becomes 1. Okay, and W and 1 is actually W. And now W or W prime is actually 1. So it ends out to be XZ. Look what I'm saying. I know using algebra manipulation may be hard. That's why most of the time our maps are going to be more systematic way or much easier. That's for sure. But still, you need to know this one. So in exams and quizzes, I will not bring something too difficult here because I know sometimes it has some tricks. Okay. So let's look at let's see another example here. For example, here I can see x is y prime z here, and also I can see this term has y prime z, right? These two terms here, y prime z, y prime z. So and this one x prime and x. Okay, that's great. So what I can do here, I can take y prime z common, and then I'm gonna have here x or x prime. Is that okay? If you look at the two other terms, also I found something common here, which is yz and yz. Okay, so and then so that means, and this one is actually 1, this one is 1. So now I have this one. Are you done, or you can simplify it more? This is a tricky part here. Listen to me. Usually what you may think, I'm done here and you stop here, and this is not the most simplified version. Okay, so we're not going to have this problem when you go to maps. Okay, usually using maps you can find the most simplified easier than here, but no, I can continue. So you can see here we have the z common. Once I take the z common here, it's going to enter by z. So it's really funny. So all this circuit is just equivalent to z. Okay, so x or y, it has no impact on the result. Always the result is equal to z, regardless of what x and y. Anyway, it's so interesting somehow. By the way, same thing here. So here, the simplified one, it doesn't have W. W does not have any impact on the result. Regardless what is W, always the result is going to depend on in X or Z. Anyway, any questions? Okay. So also I'm going to also give you more. I like to put too many examples because it helps you to understand. So let's see, for example, here in this example, I want to simplify this one. Again, I notice here we have AB prime here, AB prime here. I take it common. So now now I have C prime or C, it becomes 1. So now I was able to, same thing here. I find AB common, AB here and AB here. Also, I can simplify this one. So now I'm here. Now you can listen to me, guys. Very important thing. So now this is this expression, or I can stop here if you want to stop here, or you can simplify more to get this one. All of them are going to give you the same result. So they are equivalent. So if you implement using this one or this one or this one, it will give you the same result. They are equivalent. But usually you look for the most simplified one. Okay. So yeah, so now I'm gonna also, you can see here, if I take A common here, I can reduce it more to here. Okay. And now if you come here, this is maybe I want to explain this one little bit. This is always remember it. This is the theorem you always forget because it's not in the normal algebra. So I want to here explain it. So it's A or, okay, A prime BC, okay? So I'm gonna do distribution here. I can do distribution, so it becomes A or A prime and A or B, okay? And A or C. Is that right? Or let's just do step by step. So for example, here, I'm not, you can do this way for sure, but I'm gonna take it step by step. So I'm gonna take only this term here. So it's gonna become A or A prime, okay? And, sorry, or, because you have or here, sorry, and, but this is the or is here, okay? A or BC, for example, okay? So it's like, I'm gonna take one term and another term here, this way, okay? And this one here becomes 1, so this one is gone. So, and I'm gonna end up with A or BC, okay? Anyway, for this one here, for this one, let's also take a look at this one. For this one here, first of all, there is something I can eliminate quickly. For example, here you have C and C prime. C and C prime is 0. 0 or anything, so I was able to eliminate this one quickly, okay? Now I have this one here. So what you can do here, you can do, this is similar to normal algebra, you can do distribution. You can do distribution. For example, here, this A is gonna multiply it, sorry. So here I'm gonna distribute what I did here. I distributed this one here, and also I distributed here, as we see here. Okay, so I distributed this one here, and here multiply this one here, and multiply. It's not multiply, it's end. Okay, and then when I input here, I input this one here. Okay, I'm gonna get here. Let's look at this term here. Okay, so AB prime or BB prime. So BB prime is gone. Okay, and now look at this one. You know this is one of the theorem we have. If you have A or something and then A or something else, the result should be A or BC, right? This is one of the theorem you have. Okay, so yeah, so I got this one here, and then because I eliminated this one, this is the result. Can I simplify it more, or this is the most simplified version? Maybe you are gonna stop here. This is maybe difficult part to know if this is the most simplified or not. K-maps is going to be easier. In K-maps, it's going to be easier to find the most simplified one. That is why most of the people actually are using K-maps, but still it's expected in this course that you can also do algebra manipulation, but I don't think this will be the main focus. Okay. So now, yes, I can do more simplified very quickly. So I can see something here. A is common. Okay. And then by this way, one or anything is 1. And A and 1 is actually A. Anyway, any questions? Okay. Now I'm going to talk about something else here. We call it complementing a function. Okay. So if you have F, how can you get F prime? So what this means, if you're complementing a function, okay? It means, for example, here, if I have, this is F1. Okay, how I can get the complement of F1? So I'm going to call it F1 prime. So this should be equal to X or YZZ. This is F prime. Is that okay? So complement a function means you just complement it. Okay, here. This is F1. This is F1 prime. Okay, you complement it. Okay, then you after that you can use De Morgan just to. You can use De Morgan after that. If I want to use De Morgan here, so it becomes X prime and Y prime Z prime this way. You can use De Morgan again here. De Morgan, you can use it here. So X prime and Y or Z. Okay, and you can stop here if you want. Okay, but on the truth table, what it means complementing a function. Okay, I'm going to tell you what it means. So if it is F here, F prime is going to be flip. You flip just the bits because this function is the complement of this function. That means if this function gives you 1, the other one should give you 0. If this function gives you 0, this one should give you 1. Okay, that's why. How can you know this function from the truth table? How can you know this function is complete? So you can see 0, 1, 1, 0, flip. You flip, it's always flipped. Is that okay? That's the meaning of complement of a function. So I give you one example here. Is another example here. I have this function f. I'm asking you to calculate f prime. So as I told you, I'm gonna use De Morgan. So this is f is here. This is f, and then I'm gonna take prime for f. Okay. Then as you see here, I used De Morgan. In De Morgan, as you know, I need to calculate the inverter of this one, and then because this is OR, I'm gonna make it AND, and then I'm gonna calculate the inverter of this one. Okay. This is the first De Morgan. Now I can apply De Morgan again, but this time one time here and one time here. Apply it again. So after I apply again, I got something like that. Okay, here what I'm doing, I'm simple. You can stop it if I don't ask you to simplify. You can just stop here, and that's it. Okay, and this is f prime. So this is a complement of f. Okay, but if I want to simplify it more, okay, you can do Boolean algebra manipulation as we did before, and then after that. So anyway, so what I did here, I just did manipulation here. I can tell you what I did here. So what I did, you can see I made distribution here. I made distribution. So for x and for each term of this. So this is the first part after doing distribution, second term, third term. So just I did distribution. After I did this distribution, I find this term here is 0. This term is 0. Y and y prime is 0. So I got rid of them. Also, I find something interesting here. I find 4, 5 terms that have x common. Okay. So here, this x here, x is here, x is here, x is here, x is here. Okay. I'm gonna get x common outside here. You know, very interesting. So, and 1 or anything is gonna be 1. Okay, 1 or anything. So that means, pay attention to this. That means if you have x or xb or xc or xabc, whatever, you got what I'm saying? So if I take x common, all of these are cancelled. Because when you take x common, it becomes 1 or something here. And 1 or something is going to be 1, cancelled. You got what I'm saying? So that's why all of these are actually 1. That's it. So I go this way. Anyway, so now we have f this way. I calculated f prime. I got this one f prime here. Is that okay? I want to prove. Is that correct or wrong? Maybe it's wrong. How I can make sure it's wrong? How can I make sure it's right, not wrong? Got what I'm saying? How I can make sure? Very simple. Truth table. Create a truth table. So what I did here, I created the truth table. So here, and then I made f. Is that okay? After I made f, I got the complement of f. So this is giving me this is so again what I did, I implemented f. I got the complement of f. I got this formula. Is that okay? The second thing I can do, I'm gonna implement what I got here. Okay, I put it, and then I find it's the same. You got what I'm saying? So again, all what I did, I got f first using this formula. Using this formula, I got f, and then I complemented to get f prime. Then I did this one here, and I found they are the same. That means it's true. Any questions? Okay. Here I'm going to leave this one to you. Here I'm telling you how can you calculate the complement and simplify. So again, it's basically, first of all, you have to use De Morgan. After De Morgan, you can do some simplification. So I'm going to leave this one. I put a lot of examples. Okay. Any questions? Okay. So so we finished almost everything. We have only the last section here. Okay? But let me tell you what I have explained so far and what is missing. There is something important, very important. I didn't explain it, and very important for sure. So, and this is going to be the last one. So let me go back here to tell you from the very beginning what I did. So what I did here in this chapter, First of all, I define the three basic operations. Is that okay? How they work and so on. And then I told you, using the three basic operation, you can create function, okay? And then also here, I told you, this function, you can draw a figure for this function. Also, you can implement it using truth table. So that means, listen to me, that means if I have a function, it's easy to get the truth table of this function. Is that right? It's easy. That's what we have done. What I didn't explain yet is, if you have a truth table, how can you get the function? The opposite. This is the last section I'm going to explain. Okay. So what I explained so far, if you have a function, it's easy to calculate the truth table. What I didn't explain yet, if you have the truth table, how can you get the function back? You got what I'm saying? But someone can ask me, okay, but wait a second. Okay, I agree. You didn't explain it, but why we need it? Usually I have a function, and then I get the truth table. Usually it should be this way. So why you are telling us sometimes I can have the truth table and then I need to get the function? No. Most of the time you have a truth table and you want to get the function. You know why? I'm going to tell you why. Because if you want to design a circuit to do something, you start from you create the truth table first. When the input 0, 0, I want a function to give me a certain value. You are designing a circuit. Okay. I can give you a very quick example. Okay, using even this one. Okay. For example, I wanna design a circuit. This circuit should give me 0 if the input, for example, less than 3. Okay. Otherwise, should give me, or less than 2, less than or equal to. Okay. Otherwise, give me 1. For example, so I want to design a circuit. This circuit has input AB, and then the result should be 0 or 1. It should be, if it is less than or equal to, should give me 0. Otherwise, give me 1. Just an example. Okay. So how can we do that? All what you have to do here, you have, I don't know the function for sure, but here I know, because this is 0, 0, and 0, 0 is less than or equal to, so the result has to be 0. Okay. Now this one is 1. Okay. So, and 1 is less than or equal to, so the result has to be 0. And now this is 2, so the result has to be 0 as well. This one here, the result should be 1. Okay. So now, after I decided what should be the output of each input, now I want to design the circuit. So what gates I have to use to give me this truth table. Okay. So anyway, I'm explaining to you right now is why sometimes I have the truth table, not sometimes, most of the time, I have the truth table and I want to go back to get a function. Is that okay? And this is what I'm going to explain in the next topic. So anyway, any questions? Okay, good. Okay, so here I'm in this section, I'm going to explain to you how can, using a truth table, how can you get the function in 2 different formats. One format, and then also I'm going to tell you why we need these 2 formats. But for now, let's focus on the 2 formats I can get. So the first one, we call it sum of product, or SOP, sum of product. Okay, or you can get the function in product of sum. 2 different formats. So again, I have a truth table. I want to calculate the function of this truth table. Okay, I can do it in one of 2 formats. One form is called sum of product, the other one product of sum. Is that okay? So first of all, I'm going to explain what are these formats. Then I'm going to explain how can you do it. Okay, let's start with the first one here. You can tell from the English name, sum of product. Okay, so this is sum of product. By the way, listen to me. The term here is somehow misleading or confusing. We don't have sum, we don't have product. We have and or. You get what I'm saying? So here, what we mean by sum, I mean or. Okay, I don't know, they are using this term maybe because this term is just popular in normal algebra or whatever, but we don't have here sum or product. Okay, so sum here means or, product here means and. Okay, so this is the form I want to get it. So and, so one term or more than term, that's it. here in this format, you should see one term or one term or one term. And every term here, it can be only one variable or it can be multiple variable, but the relation between them is and. Okay, that's why this one is okay. This is sum of product. This one is sum of product. It's okay. This one sum of product. Okay, so that means again sum of product means we have number of terms, the relation between them all. Every term can be only one variable or more than one variable, but the relation between them only n. This one here is not sum of product here. This one. Why? Because this term is okay. This term is not okay. Okay, because we have or here. It has to be only end. Okay. Anyway, so this form we call it sum of product. The other one here, I'm gonna jump here. The other one here we call it product of sum. Again, similar to what I have just explained right now. This one is actually one term multiplied. Again, multiplied doesn't mean multiplied, it's and. Okay, with another term with another term. So the relation between them product, or here it means and. And every term here, it can be only one variable or it can be multiple variables, but the relation between them is and. Is or, right? Sum. So something like that. So this is product of sum. This is also product of sum. This one is not product of sum. Okay, because again, have one term multiplied by one term or and with one term, and everything here has to be this one is okay. So this is one term and this is one term. Every term can be only one variable or it can be more than one variable, but is using only or. Okay. Any questions? Again, what I'm saying, guys, here is I'm gonna give you a truth table, and then I'm gonna ask you need to find the function. Okay, you need to find the function of the given result. Okay, of in the truth table in one of two formats. One is called the product of sum. The other one is sum of product. Two ways. Okay. So also here I'm gonna tell you why you restrict me. It has to be this way or that way. What is the reason for that? Is there a reason? For sure there is a reason. I'm gonna tell you what is this. First of all, let's talk about sum of product. Sum of product can be implemented this way because the relation is always we have here or. I told you it is actually one term or one term or one term. So now I can use only one or, as you see here, and then I can use multiple ands here. So it's going to be two levels. So regardless how it looks like, it's going to be two levels. One level for and the second level only one or. You understand what I'm saying? So for example, if I want to do this one here, so this one here, I'm going to have one or. Always we have one or, two levels. Multiple ands, one or. Always this way, okay? And then here I'm going to have how many ands we have here? We have 3. 1, 2, 3. Okay, and then you can put the input here. This is how can you implement sum of product. So sum of product can be implemented using number one or multiple ands, okay, and one or, only one or. Okay. Product of sum, how it can be implemented. Product of sum. Product of sum, as you see here, we need one and. So okay, so here I have one term, and then this is one and here. Is that okay? And for every term, I need or and then and. One and, multiple or. Okay. Conclusion. Sum of product is implemented using one or multiple ands. Also, it is implemented in two levels. One level and then another level. It's good for propagation time because it's going to be only two levels. Okay. Same thing here. This one, if you do it using product of sum, so this one we need only one and then you need multiple ors. Also two levels. So regardless how big is the function, always it's two levels. Yes. So it's never going to be. No. by definition, it is one term and one term and one term and one term and one term. You got what I'm saying? All of them are connected using only one end here. And the number of OR I need is equal to the number of terms. So I need one OR here, one OR here, one OR here, one OR here. That's it. Yes. If you put it in this format, you are gonna make it this way. But if your function in a different format as we did before, it's gonna be different. So if I go back, I did before, it was not sum of product or product of sum. So that's why we had different functions before. But anyway, okay. So again, let's come to the main point here. Okay, the main point. Again, guys, all what I said, guys, I wanna put my function either in product of sum or sum of product. Okay, and you told us this is because I can do it using one OR, for example, and multiple AND. Or it can be one AND, multiple OR. Yes, I can do this one. However, this is the interesting, this is the main part here. The main part is if you have one OR, multiple AND, this can be implemented using NAND form. So we have a NAND form, as you see here. NAND form is equivalent to this one. Man, wait a second. I'm not. Okay, so I will convince you. So look here. Give me 1 second. This one is AB. So this one AB. This is CD. And then this is the result you get here. Okay. I can implement the same one here using only NAND. Using only NAND. Okay. So I can simply, because this is equivalent to this one. Okay, let me prove to you. So here we have AB. So AB prime, CD prime. And then we have here F equal to this one. But this one is not equivalent to this one. No, it is. Just to take De Morgan, ask De Morgan. So if you take De Morgan, we have AB prime, again, prime is coming to it, or CD prime, and then prime again. So this one becomes like this one. Conclusion, before I take question, final conclusion. Or before I say conclusion. So here what I'm saying, AND or form is actually I can do it using NAND. Same thing, or AND form, this one here, or AND, which is used in product of sum. Product of sum is equivalent to NOR. This one, NOR. Let me tell you the conclusion in one sentence. Conclusion is, I wanna represent my function in sum of product or product of sum. For what? Because if you implement it using sum of product, like this one here, sum of product, I can implement the circuit only using NAND gate. And this is something I think manufacturer like to do. If I have NAND gate, and then I want to implement everything using only one gate, one electronic gate. NAND gate. So I can implement everything using only NAND gate. Same thing. If you have product of sum, like this one here, if I put it in product of sum, I can implement the circuit using only one gate, NOR gate. If I have one good electronic for NOR gate, I can do everything using this one. Okay. This is the importance of NAND and NOR. Okay, I can implement it, but to do that, I have to put the function in sum of product or product of sum format. Yes, you have a question? This one here? No. This part here? Yeah, which is the first input. So the first input here, AB prime. The second input here, CD prime. Is that okay? And then the output here is going to be the two inputs AND together and then prime. That's how NAND works. So here, oh, no, it should be here. Yeah. Okay. And then you put this one in. So if you do the, oh no, this is okay. I'm gonna correct this one again. I just got some slide from somewhere, but yeah, thanks for this sketch because it's gonna confuse the student. So actually, yeah, this one is not here; it's here. And then if you do De Morgan, so it's gonna become EB or CD, which is equivalent to this one. Yes. Thanks. Any questions? Okay. So now, guys, to make it simple, so what I'm saying right now is, I wanna put, or I wanna represent the function in one of these two formats. We all the time we will do that. Why? Because if I do it using sum of product, as I told you, so this one is gonna be, I can implement the whole circuit only using NAND gate. Not only NAND gate, guys, it's a 2-level NAND gate, 2-level, not more than 2-level. You get what I'm saying? Only 2-level NAND gate. And if you put it in the other format, it's going to be 2-level NOR gate. NOR gates. So for it does, okay, if you think about logic, it doesn't matter for me in logic, but it matters in electronics. I connect logic with electronics because the people of the electronics, it's going to be much better for them if I put more effort here to create a function that has only NAND. Because I'm saying it's good for them. So it's not for logic. It's because in logic, both of them are going to give you the same result. But I want to do everything in NAND because this is good for electronics. Okay. Anyway. Any questions? Yeah. So this is the summary I have here before I move forward. So let me read the summary. Any logic function can be represented in sum of product and product of some forms, okay? Any logic function in sum of product form can be implemented in the 2-level, okay? And or NAND, okay? Because I told you and NOR, we have equivalent one for and or for NAND, okay? Any logic function in product of sum, okay, can be implemented using or and or NOR, okay? Any questions? Okay. Any questions? For free. I'm not gonna charge you if you ask a question. It's for free. First time for free, okay? I wanna make some money. Any question, guys? Anyway, so until the rest of this chapter, I'm gonna explain to you, given this table, this truth table, how this is the function I want to make. This is the function. How I can this is the function in truth table format. This is a function in one side zeros. So how given this table, how I can create this function this way using logic gates. Okay, so that if you implement this function, it's going to give you this truth table. What we have done so far is the opposite. What we have done so far, given this format, the function, you give me the truth table here. Okay. Now I want to do the opposite, and I told you why. Because when you design something, you're going to start from here. Okay. So now it depends on what you want to design. If this is the input, what output do you want? 1 or 0? It's up to you. What do you want? And then once you finish this one, I need to make it a function. Is that okay? So now, until the end of this chapter, I'm going to explain 2 things. Number 1, given this one, how I can make sum of product form out of it. Number 2, how can we make product of sum out of it, okay? So let's start with the first one here, sum of product. I'm going to start with sum of product. And sum of product here, number 1, I'm going to only work on the ones, not zeros. That's number 1. For every one, I'm going to have 1 term. And then I'm going to OR them together. Again, say it again. Okay. Number 1, this is F here. Again, this is sum of product, not product of sum. Because in product of sum, I'm going to work on the ones, not the zeros. Sorry, I'm going to work on the zeros, not ones. I'm sorry. Okay. But let's start with the first one, sum of product. In sum of product here, guys, I'm gonna work on the ones, not zeros. Okay. For every one, I'm gonna get one term here, as you see here. So how many ones we have here? Okay, let's see. 1, 2, 3, 4, 5. So I'm gonna have 5 terms. 1, 2, 3, 4, 5. And then they are connected together using OR. Okay? This is some product, as you see here. Okay, so number 1, try to locate the ones. Number 1, number 2, for each one, you have to convert this one to a term. One term, and then all them together. But how we are going to convert each one to term? I'm going to tell you how. Look here. Look, I'm going to explain the approach, and then I'm going to explain what is the logic, why you are doing that. But let me finish explaining the approach. So look here. So you are telling me this is 1, right? Yes. So this one should be represented by 1 term. Yes. This is 1 represented by 1 term, and then you do same everything here, and then after I get all the terms this way, I'm gonna OR them together. That's true. So now the question is that if you have this one, how I can get the term associated with this one? I'm gonna tell you how. Look here. Given this input, okay, this term, I want this term to give me 1. They give me this one. So this one is gonna come from this term. Wait a second. Okay, look here, guys. For every 1, I have 1 term. I'm gonna select this one in such a way, giving this input, this term is gonna give you 1. So when I have this input associated with this term is gonna be 1. Everything else is 0. And because the relation is OR, it's enough if 1 term gives me 1 and the other one gives me 0. So again, this is the logic behind it. So the logic behind it is here, this term is associated with this input, okay? So when I have this input, this term is gonna become 1 and the other terms are gonna become 0. And at the end, I got 1. When this input comes, this term here, which is actually this one here, is 1 and the other one are zeros. And I got 1 because the relation is OR, right? Okay, but wait a second. So the question is that now, this is the logic. So the logic behind it is, for every 1, I have 1 term. And then OR everything together. This is the logic. And I'm going to select this term so that when I have this input, so this term is 1, the other terms are zeros. And then because the relation is OR, I'm going to get 1. When I have this term, this one is 1, and the other ones are zeros. I'm going to design it in such a way, when you have this input, this term give me 1, right? Okay, but how you are going to do this? I'm going to tell you how. Look here, guys. If you have this input here, this way, how I can select this term so that it gives me 1 when I have this input? Using, for sure, I have to use AND, because this is some of product. So every term has to be AND. Okay? I told you before, if you have AND, 3 terms this way for AND, the only way to get a 1 when the inputs are 1s is the only way for AND. Okay, so in order to do that, okay, B, you are 1, so you are welcome to enter B. C, you are 1, you are welcome to enter. A is 0. No, I'm gonna input here is a complement of A. You got what I'm saying? So the way I'm gonna do it is, if B, I'm gonna make it A prime BC, so that all of them are become 1, 1, 1, 1, 1, 1, 1, 0. Okay, let's have another case. For example, here, let's look at this one. 1, 1, 1, 1. How I can calculate this one? That's a very easy case. I wanna design AND gate to give me 1 when I give this input, when I have this input. Okay, A, B, C, that's it. When A is 1, so all of them are gonna become 1s. Let's have another case. For example, if I wanna do this one here. Okay, how I can make AND gate to give me 1 when I have this input here? Okay, in order to when we have this input here, okay, so A, it's 1 already 1. So again, any variable that is 1, you input this variable. any variable that is 0, you have to input the complement of it in order to make it 1. Okay, because I want to get 1 when this is the input. Okay, so this one should become A, and then B prime, and then C. Okay, very easy. So all what I have to do, guys, I just explain the logic behind it. But if you need like a shortcut, or just I want to say it in just one sentence here, in one sentence, guys. Okay. Number 1, you need to locate the ones. This number 1. Okay. I'm not gonna work about on zeros. I'm gonna only work on ones. Okay. Number 2, each one should contribute by one term here, and everything connected together using OR. This number 2. Number 3, to calculate this term, you have to calculate it this way. Okay. If it is 1, if you have 1 here, so I'm going to use the same variable. If it is 0, so I'm going to use the complement of this variable. So it's going to be, and it has to be AND A prime B C. Let's look at this one here. This one, A, because A is 1, so it's going to be A, B prime, C prime, this way. Any questions? What is the logic behind it? The logic behind it is, I designed it in such a way that if I have this input, this term is gonna make 1. The other ones are zeros. Then because it's OR, I'm gonna get 1 at the end, right? I designed it. So always for this, what about this ones here? You only look at this one, but you didn't look at this one. Okay, look here. Guys, listen to me. I selected this term so that it gives me 1 in this case. In the other case, 0. So I don't need to do anything about it. You can say. So because this one is designed only for this case. Okay? So for any other case, so for example, here in these 3 cases, all the terms are going to give you 0, 0, 0, 0, 0, guaranteed. Right? In this case here, this term is 1, the other terms are zeros. And I will get 1. That's 4. Okay? In this case, this term is 1, the other ones are zeros, and so on. Got what I'm saying? Any questions? So what I did here, I got the function here. This function here can do this truth table. Okay. But be careful. This function is not simplified. Simplification is a different issue. I just need now. What I want to do now is giving these ones and zeros how I create the gate. It's not simplified yet. Okay. It's a different issue. But let's focus now on this one here. Okay. This is for sum of product. If you look at product of sum, okay, quickly, but for sure, we still have 2 minutes. Okay, so this is for if you want to do sum of product. If I want to do product of sum, okay, number 1, look here, guys. I'm gonna work in this one. I'm gonna work in zeros, not ones. I'm gonna work on zeros, not ones. I'm gonna tell you what is the logic, but let me finish, okay? And then here, because we have here 3 zeros, I have 3 terms. 1 term, and this is again, this is product of sum. 1 term or yeah. So it's product. So and. This is how it looks. So now I have 3 zeros, so I have 3 terms. These 3 terms are connected together using and. This product of sum. Is that okay? Every zero here, every zero is gonna contribute by one term here. Okay, it looks similar to what you have explained right now, but the difference, instead of working on 1, I'm gonna work on 0. Yes, that's true. Okay? There is another difference. Listen to me. Because the relation here is and, the relation is and. Okay? I'm gonna design this term so that this term, if 1 term is 0, the result is 0. If 1 term is 0, the result is 0. So here, I'm gonna, when I select this one, when I convert this one, remember, this is product of sum, so I have to use sum, not product like this one. So here, when I find the term for this one, so number 1, you have to use you have to use or, right? Because this is product of sum, right? Number two, I have to find what uh, or relation is going to give me zero in this case. So actually it is A or B or C. So this is the first step. Again, wait a second. Here you used the and. Now we are using or. Yes, because this is sum of product. This is product of sum, which is different, right? So now I have to use yes. This is number one. Number two, here, the idea is that I want to get zero. In order to get zero, I have to make sure this term is going to be zero when I have this input. So when I have this input, so you have here three terms, right? For each zero, one of them becomes zero, so that I'm going to get zero. So I'm going to design this one so that this term is going to give me zero here. I'm going to select this one so that this term is going to give me zero. I'm going to design this one so that this one is going to give me zero in this case. And in any other case, it's going to give me one. Anyway, that's enough for today.